So, good morning, everybody, and welcome to this presentation in which I will talk about a non-intrusive approach for floating point bit width optimization in the context of approximate computing. So, when it comes to computation, there are several ways to do it. First, the conventional and traditional computing ways, which always computes precisely by paying too much in terms of hardware-software complexity, inefficiency, and slowness. This is the case for critical and real-time systems such as automotive, aeronautics, and healthcare, for example. One of the emergent paradigms is the approximate computing, which consists of trading the precision against simplicity, efficiency, and speed. And this paradigm targets fields such as image processing, gaming, AI, and others, which are intrinsically error-resilient use cases. So in our case, we target approximate computing in CPU-based architectures and mainly open source RISC-V implementations. More specifically, we target floating points. In this paper, we focus on computations only since they are intrinsically approximate. Of course, there is also a potential impact on data transfers, but we don't cover that in this work. And as a matter of fact, floating point units are available in most CPUs nowadays, since they boost the performance and they enhance software portability and flexibility. So a source code can also be reused almost without changes while porting from one architecture to another. And also design time is much smaller when using floating point to implement algorithms instead of, say, fixed point, for example. However, floating point units are responsible for extensive hardware overhead. They consume a lot of power and they contribute massively to area and memory footprint compared to their integer counterparts. To illustrate that, consider the architecture depicted in this figure. This is a three-stage RISC core from ETH Zurich. It has an optional FPU that can be activated or deactivated at synthesis time. And around 44% of the area of the core is actually taken just by the floating point in its register file. So there is a serious need for reducing this overhead to find the middle point between all advantages brought by floating points versus their expensive cost. And as you know, a floating point number is represented by three fields: the sign bits, the exponent field, which represents dynamic range, and then the mantissa field, which represents the precision of the representation. We will denote the couple EM, the floating point format, where E is the exponent bit width and M is the mantissa bit width. One of the techniques to reduce FPU overhead is simply reducing the precision of the floating point representation used in a system. So we can, for example, do that by using either single precision 32-bit or double precision 64-bit or even half precision 16-bit FPUs. And those are IEEE standard formats. Or we can also craft arbitrary formats that adapt to our need. For example, if we only need more precision, we can only increase M, the mantissa bit width. If we only need dynamic range, we can increase only the E, which is the exponent bit width. Now, we have all these formats that we can use, but the problem is, for a given application and dataset, what would be the smallest configuration possible that will satisfy a given quality of result constraint? So to answer that, we need tools and methodologies to simulate floating point approximations impact at application level. So in the remaining of this presentation, we will see What are the existing works that provide tools to simulate effects of floating point approximations? Then we will present our proposed approach and implementation of this approach and its evaluation, and then we will conclude with challenges and future works. So to study the impact of floating point approximations at application level, there are several works in the literature that propose tools and libraries, such as MPFR and GMP, which enable emulation of higher precision as well as reduced precision. These are most efficient when hundreds or thousands bits of mantissa are needed, for example. There is also FlexFloat and FloatX, which are part of the European OperaComp project, and these are libraries mainly intended for reduced arbitrary precision. Now, to illustrate how these libraries are intended to be used, consider this example where I declared a few variables and I perform a simple multiplication addition. So D equals A times B plus C. To write this in MPFR, we should first declare some special data type variables and perhaps temporary variables to compute intermediate results. Then choose a precision for each one of them, and then initialize the variables, and then figure out the dependencies for each operation and compute in the correct order. So you can see already that things get more messy once we start dealing with more complex applications. So in conclusion, most of the existing tools are intrusive to source code, meaning that they require the code to be transformed or rewritten. This could be feasible for applications written in advanced languages such as C++ and Python, where the programmer can actually benefit from concepts such as operator overloading, inheritance, templates, etc. Also, it does not preserve existing software stacks, and it increases the design time. And even when it's done right, they still rely on higher precision hardware to be executed. So for reduced precision, it's only intended for simulation, and the code cannot be reused as it is. So what we really need is tools or approaches that enables the study of the impact of approximations, but in a non-intrusive way that preserves and reuses the existing software stacks. Now for the proposed approach, the approach we propose in this work is to introduce floating point approximations at assembly interpretation level by changing the semantics of assembly instructions. So to visualize the idea in terms of hardware, consider an assembly instruction finst with operand registers RS1, RS2, and RS3, and output destination register RD, and a given rounding mode. Then consider the FPU that will execute this instruction. Usually the FPUs are IEEE compliant, which means that they are either 64-bit, 32-bit, or sometimes 16-bit long. The FPU performs computations and also conversions from integer to floating point and vice versa, as well as conversions from one floating point type to another, as well as other operations. So in our case, we are only focusing on the computational operations such as addition, multiplication, square root, etc. And the proposed approach consists of first performing a reduction from the original format to an intermediate reduced format. Then we perform computation in the reduced format, and then we extend back the result to the original format in order to keep consistency with the rest of the system. So as you can see, the computational part will be reduced drastically. Also, power consumption will decrease. since the reduce and extend logic is pure combinatorial. So the only potential drawback would be an increase of timing. Now to illustrate that, the idea, consider the same example we saw earlier where we have the statement D equals A times B plus C. Compiling this would generate an assembly instruction that performs fuse multiplication addition. So I say mod.d to say it's double, D for double. And then at runtime, instead of interpreting this instruction normally, where the destination register receives RS1 times RS2 plus RS3, instead of that, we execute it in an approximate way by performing the three steps we talked about. So first reduction, then the computation in reduced format, and finally extension to the original format. So the idea is to still compile normally, but then introduce approximation at runtime. We can even do that actually dynamically, but we don't cover that in this paper. Now, among the advantages of this approach, as we said, it's not intrusive to source code at all. The existing computational kernels and software stacks are preserved since only the interpretation changes, not the software itself. Also, the application can still operate in full precision. So for the implementation, the approach can be experimented either in software for fast quality of results design space exploration, or in hardware for hardware overhead versus quality of result design space exploration. Now, for the implementation, we implemented this approach in QEMU, which is an efficient dynamic binary translator, where instructions are emulated in software. QEMU is scalable and extensible, so the approach can also be ported to other architectures such as ARM, x86, MIPS, etc. And it is capable of running Linux applications as well as bare metal libraries. So it can also run multi-core and multi-threaded applications, and all these features and others make it the best candidate platform to implement the approach. Now, QEMU operates by taking as an input a RISC-V executable binary. It translates it to an intermediate representation where each RISC-V assembly instruction is emulated by a C function, in this case helper fmod_d. So inside this function, we need to replace the original behavior that performs the fuse multiplication addition operation it replaces that by the approximate one, just as we did in the earlier example. And under the hood, flex float is used to express the approximate behavior. Now, in addition to the executable binary, the simulator can also take an input dataset, and then the exponent in mantissa bit width parameters through the command line at launch time. And this will enable us to explore how a particular FPU configuration would impact the numerical outputs of the executed application with regards to this dataset. Now I'll talk a little bit about the evaluation. So to evaluate our approach, we selected a set of benchmarks from the approximate computing state of art. And for each benchmark, we consider an application-specific metric that is computed based on the final results. We consider mean relative error for Black-Scholes, root mean square error for SBench and FFT, and miss rate for Germain. The way we will proceed is that for each dataset D, we execute the application in full precision and the obtained numerical results will be our reference. Then for each reduced configuration, we will run the application, get its numerical results, and then compute the metric with respect to the reference. The results are then analyzed using a Python script where we can choose either standard metric one or such as MRE, RMSE, or it can also be user-defined. And the way we will represent that is using a heat map where horizontal axis will represent the exponent bit width. The vertical axis will represent the variation of mantissa bit width, and the colors will represent the intensity of the error. Now, once the reference configuration is executed, we get a result. In this case, the error is 0 since it's the reference 64-bit FPU. And we repeat that for all possible configurations in design space. So you can already see that the effect of varying each parameter on the results of the application. In this case, you can see that error only varies with mantissa. As long as the mantissa bit width is higher than 22 bits, the error is 0. And this means we do not need a 64-bit FPU to execute this application with this particular dataset. So if we want only standard formats, 32-bit floats are sufficient for this case. Otherwise, we can reduce down more to 29 bits and still keep 0 error. Of course, if the quality of result constraint is relaxed, we could reduce more. Now, doing the same for main, in this example, the same observations apply to this case also, but we can even reduce this time until 24 bits. The only difference with FFT is that this time the exponent also affects the quality of results. Now, to summarize, we are able to find the smallest configuration that verifies an error constraint equal to 0. And now, since we are introducing variable precision behavior simulated in software, the total simulation time will be affected, of course. And the execution time can be 2 times to 12 times higher than standard precision simulation time. But still, this simulation time budget is not critical and it is affordable. And before I finish, I will add just an additional example, which is a convolutional neural network pre-trained with the CIFAR-10 dataset, where 500 images of the dataset have been classified, and here we present the success rate for all FPU configurations. It turns out that even with an aggressive bit width reduction, FPU from 32-bit down to 8-bit, the accuracy drops from 71% to 68%, which is very negligible. This confirms that CNNs are actually among the best targets for approximation, and this is a fact that has been confirmed in a lot of state-of-art works related to neural networks. Now, for a conclusion, we established a non-intrusive approach that evaluates the impact of floating point approximations at application level. The approach, as we saw, is extensible and scalable to other architectures. The approach also conforms with the state-of-art results, as we saw with the CNN application. Simulation time overhead is affordable compared to the design time of the other approaches. Concerning future works, evaluation will work on the evaluation of the hardware gains and then enable the selective approximation in the simulator in order to be able to selectively approximate specific regions of the application. And one of the axes that we want to explore is the relationship between operator level precision and application level accuracy in order to generalize this relationship for more application. Thank you for your